All right, so hello and welcome to Algorithms Live. This week's episode, I'll be discussing some techniques on Bitmask DP, particularly this rolling Bitmask technique that comes up every so often when you're trying to sweep through boards. But I've got three problems that I posted in the blog, and I'd like to do each of those today and talk about them in depth. So be talking about this FloorBoards problem. We have this problem reach for the stars that's rolling Bitmask DP. And I'll explain the first one we're going to do won't be rolling Bitmask, a different type of Bitmask DP. We'll also solve this problem Order of the Hats that I posted that's kind of it's a Bitmask DP, but a different flavor. Yes, and I'm hoping that this will be new for some of you, or at least some of these topics will be new for some of you. But before that we begin, I wanted to get into announcements. So I'm going on a brief hiatus for Algorithms Live. It's going to be about a month. But the reason being is I'll be going to ICPC World Finals. So I'll be traveling on that. And I imagine with the hotel Wi-Fi being what it is sometimes on these travels, it'll be difficult to run the show. So I'm just going to take a break. And then I'm also helping with the USACO training camp this year. And so those go back to back. So I'll be traveling quite a bit. But I'll try to be coming up with some new ideas of what to cover and hopefully meeting some new friends at World Finals that I want to have on the show and we can discuss cool problems. So hopefully the break won't be too long for you guys, but I'll be excited to come back and continue over the summer. And hopefully with some really neat new guests. So that's just the announcement I make. I should probably post something in the blog about that. And the other thing is if you are going to ICPC World Finals, please say hi. I'll be around with the UCF group. And it should be easy to find me. All right, so let's start with this set of problems. And so this first problem I want to cover is this problem called FloorBoards. So what we basically have here, so maybe I'll go like that, something like that. So we have some floor, some of the cells are blocked off. So I'll draw out some blocked off cells. Maybe not quite like that. We'll pick a few other cells. Trying to draw one of the samples. So you could think of these kind of as pillars in a room or walls or what have you. And am I off by one? Yeah, I believe I'm off by one. The grid looks something like this. And what we'd like to do is we'd like to place FloorBoards on this grid, but we'd like to place the minimum number of FloorBoards to satisfy the grid arrangement. So I might place some vertical FloorBoards like this, maybe another one like this. And I believe I can get away with just horizontal. So maybe I'll make the horizontal ones red. So 1, 2, 3, 4, 5. So in this case, I've managed to solve it using 7 boards. Going from left to right. And what I'd like to do is I'd like to make this grid, basically given the grid as input, put the minimum number of horizontal vertical FloorBoards on it so that every cell is covered that's not a wall cell. And I can't run pieces of the board through walls or things like that. So the bounds, this is, on this problem, it's a 10 by 10 grid. Some of the cells are blocked off, no restrictions there. So there are a few ways to think about this in terms of trying to attack it or directions we might go. Well, it's a 10 by 10 grid. You might think, well, maybe if I hold a cell has been covered or a cell has not been covered in the grid and encode that as my state. So this is a larger state. So I have a 10 by 10 grid. an idea that might come to mind is make 0 not used, 1 used. I could do a sort of bitmask DP, and the bounds on that would be 2 to the 10 squared, because there are 10 squared positions on the grid. And so that ends up being 2 to the 100. So that's way too big. So the first observation when you're going after a problem like this is storing the entire board state in your DP is just too much information to hold. Although there are some problems where you can get away with it. So for this problem, what we really want is this idea of sweep. And what we'd like to do is we'd like to take the grid cells, however we have our grid, and we'd like to sweep top to bottom. In particular, we're kind of going in this row major order. So these are the cells I'm going to be processing one by one. And you can just keep going down one by one by one by one by one, and explore them in row major order. So now what I need to do is I need to figure out how to cover the board, make sure every single cell is covered, and make sure I'm using the minimum number of board runnings as possible. Okay, so if I'm at a cell, if it's not a wall, then there are a few options for what could be construed as covering. I could have some board here behind me, and maybe I'm considering to extend it. So I'm like putting a horizontal board down that I'd like to take, and I can extend it to the right as I'm going in row major order from left to right. I could say maybe this cell is part of that horizontal board that's going across. And so I'll just keep a bit in my state, so 1 or 2 numbers, and 1 will just represent the board is running. So I have a board running from left to right behind me. And 0 if there's no board, no board running. So there are a few cases for that. Maybe I'm running through my DP, I'm on this cell, and maybe just there was a vertical board behind me. So in that case, there would be a 0 for the running cell behind me. Okay, and so the other thing I'll be keeping track of is if I'm at some cell, I'd like to know for the positions behind me on my current row, there might be some vertical tiles here. Maybe this is blocked off and maybe that's blocked off, but there might be some vertical tiles behind me that in the future I'd like to extend this way in the vertical direction. And then from the previous row, I'll have made decisions on where to place vertical and horizontal tiles. I could have vertical tiles here, or even a vertical tile right where I'm currently standing. And for my current position, I might consider I want to have this tile extended before moving on to the next cell. So what we're going to do is we're going to look at every single column, and we're going to make what's called a mask. But it's basically a binary string 1 or 0, and the ith bit, so this is 0th bit, 0th position, 1, 2, 3, 4, and so on. That ith bit that's on in the mask is going to represent 1 if there's a vertical board that we're considering running down from top to bottom, and 0 if there's not. So there are basically 2 things that could have happened there. It's either a horizontal board at that position, or it's a wall. And so the mask state, we basically have 2 to the 10 possible bit masks that can be behind us, or 2 to the number of columns if you wanted to generalize this a little bit more. And so that's the basic idea with this bitmask DP. We're going to try to keep track of the boards vertically that are running down that we'd like to place onto this grid, and keep track of the board that's behind us. So our DP state looks something like this. So we have one position that is 0 or 1. That's basically if the horizontal board, this piece right here for behind us, is on. And then we also need something for the row and column. That's also part of our state. So that's 10 by 10. And then the last piece is just our mask of the previous row. And if it's behind us, it's also the next row. So that's 2 to the 10 in terms of our state. And so our transitions, or our choices at every single state, are going to look something like this. We can either start a new board. So it's either if it's a vertical board, it's the top left corner here. That's where I'm going to start that vertical board. Or it's a horizontal board, and this is where I'm starting that horizontal board. So my case here is starting a new board. So that's horizontal and vertical. Those are my choices for starting one. Or I can continue a board, and I might be able to continue a horizontal board or a vertical board. And that's what we'd like to maintain in our DP. Okay, so that's the basic idea for this bitmask DP. So I'm actually going to go code this one. I've got topcoder up, and I'll just show you how I code this kind of bitmask DP. And so this one isn't a rolling bitmask. You could almost call it a static bitmask. It doesn't really have any choices for nothing's really moving around in our state. We're just keeping track of the previous row at a given time. All right, so let's see how quickly we can solve this one. So I'm going to store some width and height information. Also, an infinity value might be good. And I need to keep track of if that cell is blocked or not. So our state is whether or not the thing behind us is a horizontal board, our IJ position, and our mask. So that's going to be our DP. So topcoder, I need to get I'm just going to try to get the input into the version I like. I'll just take the input. I like things as two-dimensional Boolean arrays. Sometimes what they'll do is they'll just take the input and keep it how it is, and probably a little bit faster to code for topcoder. But that is not what I'm doing. Okay, I'll keep this as 0 for now to return. So I'll change that later. So let's talk about our DP. In terms of our base cases, what I'm going to do is I'm going to be going through in row major order from left to right. So I keep an intermediate base case. If I end up hitting the end of my row, I basically just say call the DP going to the next row starting from the leftmost column. So sometimes that just makes it easier for me to code this kind of bitmask DP where I'm sweeping from top to bottom on a grid. In this case, I've basically gone off the last row and I'm at position 0 in my array. So this is my true base case. I basically explored all the cells in my DP in row major order. And so my answer there is just 0 changes to get this floorboard to work. And I don't even care if I have boards running or not. Okay. So we have a few options here. So let's talk about our result. So initially, I'm going to say our best possible result is just infinity because we don't have any answer. But what happens if this cell is blocked? What am I going to do there? And I'll do something different when the cell is not blocked. So if this particular cell has a wall in it, what could happen? Well, I could basically lose this. If I have a vertical board running, then I can no longer have that vertical board running. And if I have a horizontal board running, well, I can no longer have that horizontal board running. So I need some extra information here. So I'm going to create a mask called missing row. what this is going to be is it's basically, I guess I could call it missing column. Yeah, missing vertical board is basically what this is. So what I'm going to do is I need to turn off the if bit in my string. So what I'll do is I'll take, if I do 2 to the w, well, that's that if bit turned on, so it's 2 to the w. So it could look something like, let's take a look here. It's 1, 0, 0, all the way out, something like that. And so what I really want is, these are all the positions of bits that I care about. I really want the mask where it's all ones. So I'm just going to subtract 1 from that mask, and it's going to basically give me the mask of everything all turned on. So I subtract out 1, and that gives me a mask everything all turned on. And then depending on the position I am in the DP, I'm just going to subtract out 2 to the I. That's what this bit shift is telling me. Because what that'll do is if I'm at position I, so maybe right here, it'll turn it into a 0. And now I have the bit mask of everything turned on except for the cell that I care about. And so if I AND that mask with my current mask, I basically have just turned off the ith bit. And so that's how I leverage having a missing column. So now what I can do is not continue any horizontal thing, move on to the next cell in row major order, and then wipe this row, or wipe this column, I guess I should call it column, from existence. And that's the idea here. All right, so let's do, let's continue the horizontal mask, or the other cases. So our other cases, we can continue a horizontal, or we can continue a vertical floorboard. So here's the case. If I want to continue a horizontal, I have to make sure that bit is on, that I've actually started a horizontal behind me in terms of my state. So that's the current result, bi plus 1j. And then I eliminate this row, or this column, I guess. Keep calling it row. But I eliminate this column because that's the column behind me. If I'm continuing the row horizontally, I'm no longer continuing that column. I also need the case where I want to continue a column. So I check my column masks for the row behind me. And if I have that missing column, so in other words, that bit is on, if I AND, so this is how you can check if a bit is on fairly easily. You take the bit mask and you AND it with 2 to the I, and you can get the answer for that particular bit mask. Min, my result, J, and mask. Okay, so that's the case where I want to continue on the mask I currently have. And so you'll see I eliminate the horizontal piece of this bit mask entirely. All right, so those are the 2 cases where I'm continuing a horizontal or vertical board in terms of placing them on this grid. The other thing I can do is I can just continue or start a new board if it's in the top left corner of my grid. So I add 1 to this transition. So this is the horizontal piece. And so I just flip that bit on, saying that I've started a board horizontally, and I'll just delete what's currently there for that column. And I can do the same thing for the row. So I'm going to continue a column vertical board here, or start a vertical board. So I need to just basically turn that bit on in the mask and say I have a vertical board that I care about that's running right now. That gives me that result. And now I need to return my result. Since this is dynamic programming, I should memoize it. So I'm going to do my classic trick for memoization. You may have seen in a previous episode. I'm just using objects in Java to do the heavy lifting for me. All right, so make our memo table. So now we just need to make the answer the call to the dynamic programming. So I initially don't have a horizontal board running or a vertical board running. I'm starting at cell 0, 0, and no vertical boards are running. Code cannot, oh yeah, char at. Like that. So code compiled successfully. Null pointer, line 20. Oh yes, it has to not be equal to null. And so I pass the test data here. So let's go ahead and submit the code. So we'll run system tests. And as you can see, it passes all tests. All right. So you can, if you want to get that code, you can go to the top coder practice room. This problem was from SRM 383, I believe. Yes, 383 div 1. So you could probably grab the code that way. All right. So let's move on to another problem and go back over here and talk about this problem called reach for the stars. So this is from the local programming contest at UCF. So that's our selection contest. And the idea with this one is this is considered a star. And so you'd like to stamp a piece of paper. Maybe that you have a piece of paper that's stamped some number of times on a grid. And what you'd like to do, so you're given a grid here. So if I stamp it once, maybe it looks like this. I could also stamp it again. So maybe I stamp centered right there. So I could stamp like this. And then maybe stamp over here. Or I could stamp centered right here. So it just fills in those locations. Stamp centered right over here. So it stamps in these locations like that. So you can get all kinds of funky looking shapes based on where you're stamping. And what you'd like to do is you'd like to know what's the minimum possible number of times that this had to be stamped using the star stamp to get the picture that you're given. So in general, if this problem is a graph and not just like a connected set graph, this problem is dominating set. So it's a famous NP complete problem as dominating set, or here's the optimization problem. So NP hard, but what you'd like to do is we'd like to recover that minimum number of stampings for a grid like this. What's nice is this is a grid you're given. It's a 9x9 grid. So I'll write out that information here. So it's a 9x9 grid at most. And the basic idea that we want to attack this with is very similar to FloorBoards, right? Because maybe I want to keep track of what's in front of me. So here's where I am right now. if I consider placing a stamp, it'll mark where I am right now and everything in front of me in this form. So maybe that's a little counterintuitive because you think of stamping at the center. But to me, it's a little bit confusing keeping track of what's behind me and also what's in front of me. So these two would be behind me in row major order, and then the other ones would be in front of me. So I don't want to keep track of all that. So I just pick the topmost leftmost cell, and that ends up keeping everything in front of me in terms of my decisions. So if I want to consider stamping a board, if I use the technique I did for floorboards, it would look something like this. And what we have here is we have to keep track of 3 rows in front of us, which that's kind of a problem. So 3 rows. And here's the reason why this is a problem. So if we want to keep a bit mask, 1 or 0, is that cell stamped or not? Well, there's 27 cells because we've got 9 for our current row, 9 for the next row, 9 for the row after that. So 3 times 9 is 27. So you have 27 cells, which means we have 2 to the 27 masks that are possible. Either a cell is stamped or not stamped. 2 to the 27 masks, that's a lot of masks to consider in terms of what's in front of me. So that's way too big, first off. So this is where the rolling bit mask idea comes in handy, because if you look at these cells, there's a lot of wasted space here. These are never going to be marked because we haven't considered these cells yet. We can't possibly mark it using this shape. And this is also wasted because why am I keeping track of what's already been marked? So this is what comes into the case of a rolling bit mask. And here's the idea for a rolling bit mask. We've already handled these cells. We get to cell I, and we want to keep track of what's in front of us on that row. We want to keep track of the entirety of the next row. Has it been marked or not? And we want to keep track of up to just shy of where we currently are, because we're considering to mark this cell, so we obviously haven't marked this cell or any of these cells in front of us. And so what you'll notice here is we need all of our current row, and then what's missing from our current row is in this row. So you can kind of combine these rows together and say they're size 9. And then this row is just size 9, so we only have to keep track of 18 cells total, which means we only have 2 to the 18 possible masks for our bitmask DP. So the cells of the mask, the 0 or 1 piece of the mask, 1 means it's a black cell. 0 means it's a white cell. We haven't marked it yet. And that's all our bitmask is going to keep track of. And we're going to have this rolling bitmask. So how do you keep track of, why is it rolling? How do you keep track of these bits as they're coming? So let's say I've got my stamp that I'd like to place. We're trying to consider placing that stamp. I'm at position 0. This is basically ij of where I am in my state. And what I'll do is the ith bit in my mask will keep track of the cell that's I steps away. So if so this is my current cell. This is 1 step away, 2 steps away, 3 steps away, 4 steps away in terms of going in row major order. And this continues until I go off the grid. I come back around, but you'll notice this is column minus 1 steps away. So I'll mark that as C minus 1. This is C steps away because it's on the next column in terms of my row major ordering. This is C plus 1 step away. And this is 2 times C steps away. So what we're doing is we're just keeping track of what's in front of us in terms of its relative position to where we are. So then when we jump from position I to position I plus 1 in our row major order, all these bits shift by 1. So if I had a mask like this, what I basically do is just divide by 2 or bit shift right by 1, and I get rid of everything that's not in that mask currently. It also makes it really easy to mark this mask with the stamp because I'll just basically turn on 2 to the 0 ORed with 2 to the C minus 1, ORed with 2 to the C, ORed with 2 to the C plus 1, ORed with 2 to the 2 to 2C. And so that basically all this together, combined together, we basically just turn on all the masks in all those positions. Okay, so the last problem I coded as a recursive DP in terms of this bitmask DP. What I'm going to do here is I'm going to do this in iterative DP because I think that will be exciting. And there are some advantages to the iterative DP. So here's a conceptual change I'm going to make this problem a little bit easier to code iterative DP. Instead of have ij positions, I'm actually going to physically label every single one of these positions in row major order. And so that way, remember when I was doing the recursive DP, if I ran off the end of the row, I just like reset it to go to the next position. If you want to do this as an iterative DP, it's much easier to just go, oh, I'm at position 4. Well, now I just go to position 5. So that's implicitly handled in terms of my state. So now my state is just position and mask of what's behind me. And so I can just do this at iterative DP. And you'll notice I'm always going from position, the current position, to position plus 1. So if you're into space-saving DPs, you can actually make this really easy as a space-saving DP to save memory. I can get rid of this dimension entirely, just store my current mask in the next position's mask. And I can do this one as a space-saving DP where the amount of memory I'm using is just 2 to the 18 or 2 to the whatever. So if the problem had smaller memory constraints, I could still solve this problem. And so those have become a little bit more popular on Topcoder. You can specify specific memory constraints or on other judge platforms. So it comes up very sparingly, though, I'd say, but it's good to know how to do. All right, so let's do this space-saving DP, and I'll show you how to code this one. It should be fairly easy to code. And I just have the data saved locally, so I'm not going to jump on a judge and run this one because I don't think this is hosted somewhere. But if I could ever get Codeforce's judge access, maybe I could add it to the Codeforce's gem, some of these old sets. All right, so let's work on stars. So I'll keep a few things here. I'll do row column instead of with height. Last problem I did with height, and I kind of did like X, Y coordinates. Here I'll do row column. So I is the row, J is the column. Some people like that better. I tend to switch back and forth. Maybe it's a bit confusing. One's more convention for matrices, and the other one's more convention for 2D coordinates. And I like geometry problems, so that's why I typically do those 2D coordinates. But then matrix theory, it's always row, then column for the order. A bit of a troubling thing. So in a sense, it's not consistent. So we'll do J column. So basically, is this cell marked in our 2D grid? So the grid is hash signs and dots. That's basically what I'm reading in. So I'm just making a 2D Boolean array. So you might ask, why did I make this can mark array? Basically, the idea is just to make my code a little simpler, I'm going to mark cells that I'm able to mark in terms of my 2D grid. So if I'm on the border of the grid, I'm not allowed to mark it with my stamp. I can't have the stamp go off that border. And if all the cells aren't colored in, I can't mark that stamp in that location. So I'm just pre-computing that information just to make it cleaner to code the DP piece. You could do this check inside the code, but I just find it's a little bit easier to do this check right here. And I'm representing the center of the stamp, but actually what I want to do is I want this can mark to be at the top of my stamp. Because I'm doing it in row major order and only stamping what's in front of me. So that's what I'm doing here. So then I just need to check to make sure all the positions around me relative to IJ are marked. So I'll just hard code that in. It also do some fancy for loops and stuff, but this is simple enough to just hard code. That's filled in. Another thing I'd like to add is usually for these kind of problems, sometimes you'll see problems on tetronomos. It's like how many ways can you place a tetronomo? And it's a similar bitmask kind of DP to this technique. So you can check some of those problems out. If I find one, I'll post it in the blog. But earlier today when I was looking, I couldn't remember where they were. But I've seen those quite often. Though they've kind of gone out of style, I haven't seen a tetronomo problem in some time. Maybe I'm not participating in enough contests. So here's what I'm going to do. I'm going to make my 2D DP be the row and column positions plus 1. So it's going to go from 0 to R times C in terms of positions here. And this is what I'd space save over if I wanted to do the space saving DP. So I just keep track of position I, only compute position I plus 1 in the DP table. And here's my DP table. It's 2 times C in size, and that's my mask. It's 2 to the 18, worst case for the mask. Okay, so do that. So basically what I'm doing here is just saying every state I can reach in my DP is just infinity. And then my base case is I'm at position 0, and nothing in front of me is marked. Right. So I need to keep track of position in row major order. That's why curcel is -1. So I'll just run through the cells one by one. And then curcel is that position value. So I increment it right away. That means that I'm starting with 0. Okay, so if I'm doing iterative DP, I have to loop over all masks from the cell. And what I'm doing is updating the answer for everything at position I plus 1. And so I'll put in an extra check here. I won't update this if this DP position is infinity. That'll help prevent integer overflow, that kind of thing. I guess I didn't save an infinity value, so I'll do that here. Okay. So next thing I can do is I have 2 options. I can try marking the cell. So I'll look at my can mark array, and this is mark cell. Don't mark cell. And those are my 2 options for transitions. So I need to look at the next mask. And so I saved a mask basically keeping track of what happens when I stamp it. So if I can mark this cell, then I'm just going to mark this cell. And what I'll get is mask, my current mask, ORed with the stamp mask. And it's a rolling mask, so I basically divide by 2, which is the same as bit shifting by 1. Ooh, it should make a next cell. That'll be helpful. I'll do next cell of next mask. So I min it with what's currently there and taking this mask plus 1 because I'm basically doing another stamping. So my DP is going to store what's after doing that extra stamping. All right, so then if I don't mark a cell, let's talk about what I need to do here. If I have my DP so far, and I'm considering not marking a cell, this is kind of what it looks like. If my image had a cell marking right here, then if I move on to the next position, then, and this was currently white, then I don't want to consider that so far. Because this was my last opportunity to mark it with a cell because I'm keeping everything in front of me. So that's no good. So if I choose not to mark something, it needs to either be blank or it needed to be marked by some stamp in front or behind me, and then encode that marking in the state. So that's what I'll do here. So I have 2 cases. So I have is marked. So it's either not is marked ij. So it's either not marked or it needs to be marked in my state in terms of my mask. Changes to it that way. So it's either not marked or it's marked this way. So that'll be that state. So I need to store next mask. I just divide by 2. And I don't have to pay anything for skipping marking the cell. And so those are my 2 options for marking and not marking. Okay, and so that completes my DP. The problem asks that I print out impossible in the case when you can't possibly mark the cells. So there's a good sample here. So let's take a look at the samples. So you'll see in this first sample, it's just a single marking. You can't possibly make this through the stamping because I'd have to go off the paper. So it's a 1-by-1 cell. So there are a bunch of special cases like that that you just can't form. And so those are just the impossible cases. So you need to detect that. And otherwise, I just look at being finished off. I make sure that nothing in front of me is marked in terms of my cells. So that's why I'm checking the very last cell that goes off the page. And I make sure nothing in front of me is marked. And if that's the case, then that's my answer. So I'll just print out the answer like so. Yeah, let's hope I don't have bugs. All right, so if you look at the problem, this is me just running the samples, so I get the samples correct. So we'll try running it on the complete set. So let's test that out. Let's see if it's correct. And just diff it with the output so it matches the judge output. So we're good. All right, so that's how you solve stars. So we're going to do one more problem now. This is going to be the last problem. And so switch back over to the black background. And what I'd like to do is this problem called Order of the Hats. Which is a bit of a different kind of Bitmask DP. So in this problem, you're given a spell chart. And so the spell chart could look something like this: some no's, some yeses. Something like that. And what you'd like to do is you'd like to, so it's basically like you have some spell I and some spell J, and a yes tells you that you have to learn spell I before spell J. So you can just think of it as a graph. So if I drew this one, I basically have a graph of spells that you have to learn one spell before another. And so the idea is you're given a spell chart, but then the story is something like some changelings came and they switched some yeses to no's, no's to yeses. So you want to make sure it's possible to complete learning all spells. So you can think of the learning one spell before another as a prereq for that spell. And so you'd like to switch no's to yes and yes to no. So you're allowed to switch no's to yes, yes to no, such that no cycles exist. So if you think of it in terms of requirements, if I had to learn this spell before learning this spell, before learning this spell, before learning this spell, then I'd never learn all these spells because there'd be a cycle in my requirement. So what I'd like to do is the min number of swaps. So it's a little bit deceptive here. With a bit of observations, we never want to change a no to be a yes. And that would correspond to adding an edge. Because adding an edge never gets rid of a cycle. So we never want to do this. So greedy observation, we always want to make yeses, nos if we can. Okay, so we think of this as a graph. This problem is actually famous. So we have a graph. You're given a graph as input. And what we'd like to do is we'd like to delete arcs, so delete edges in our graph, such that there are no longer any more cycles in this graph. So this problem has a name. It's called feedback arc set. And it's a very famous problem because it's in one of Karp's 21 NP-complete problems. So it's one of Karp's 21 NP-complete problems. So we're not finding an efficient solution to this in terms of our polynomial time solution to this. But in the problem, n is at most 20. So we could probably get away with some kind of exponential algorithm to solve it. So what I recommend doing for this problem, if you haven't seen it before, was give it a try. Try to figure out how to solve this problem yourself. So maybe pause the video if you're watching later, because it's a lot harder than it looks. But knowing that it's NP-complete, it really makes it so that you know that some greedy is not going to work. So that's my tip there. And I'm just going to try to analyze it, go through some wrong paths that maybe you could try to solve this one before we get to the regular solution. So the idea here is the first thing is a graph with no cycles is called a DAG. So directed acyclic graph, because this is a directed graph. And so we'd like to basically remove edges from the graph to turn it into a DAG. So you might try, if we want to do some kind of DP here, do we encode the cycles that we have left? It gets a little bit weird. It's like, well, what do we do? How do we encode this information? It's like, how do I do this? How do I get this information? So what you should do is you should keep playing with it. You're thinking, okay, do I encode the cycles now? How do I do this? And eventually you start thinking, okay, what are the properties of directed acyclic graphs? Well, we know if it's a directed acyclic graph, then it has to have a topological ordering. So if you remember when you do a graph, so I'll just draw out a graph here. Sample graph 1. So topological ordering is putting the nodes in an ordering so that every node is processed before its predecessor. So if I look at, so this predecessor here for 1 is a predecessor of 2. This should come before 2 in the topological ordering. And you'll see every graph has multiple topological orderings, not just one. So any topological ordering would do. And the way you extract a topological ordering, there's an algorithm for that. You can basically look for the node with degree 0 and then remove it. So in this case, I'll take the node with degree 0 and remove it. That's degree 1. So then I look for a new node with degree 0 and then remove it. So I can remove that. That's a node with degree 1. That's 3. Then I pick another node with degree 0 and remove it. And so that's 2. And 1 was also pointing to 2, something like that. So then I could pick 4 or 5. Multiple topological orderings can exist for any given graph. So 2 goes to 4, 2 goes to 5. So I remove those, and I'm left with 6. So something like that. And so that's the topological ordering of my graph. Move it to be a little more centered. Okay. So the thing you'll notice about this topological ordering is if I'm at node I, all its edges are pointing to the right. And that makes sense because the definition for topological ordering was exactly that. It has to become earlier in the topological ordering in order to have a graph with no cycles. So if we want to take a normal graph, which might have cycles, so the topological sort will fail if I have a cycle in my graph. It only works on directed acyclic graphs. But if I brute force all possible topological orderings, so brute force all n factorial orderings, then for a given ordering, I can just delete anything going backwards, any backward edge that occurs. All right, so n factorial is too big for 20. That's way too big, so we can do dynamic programming. And so this dynamic programming, if you've ever seen the traveling salesman Hamiltonian path DP, that's exactly what we're doing here. So if you haven't done one of those problems before, you can take this idea and solve one of those problems. It's pretty much the same idea. So our state for doing it as a DP is I keep a track of a subset of the nodes placed. You can think of it as a visited array. I basically, what nodes have I seen so far? But I'm just going to use a bitmask to keep track of that instead of an array of positions. And then my transition is just placing a new node. Okay, so we can look at the nodes placed. So maybe I've got some nodes that are being placed in my topological ordering, 3, 8, and 9. Well, if I've already calculated the cost for putting them in whatever order these are, then 1, 3, or 1, 8, 3, 9 is going to end up having, it won't really matter in terms of the next node placed, what order these were in, as long as I just, for the nodes I've already placed, the subsets of nodes I already placed, so 1, 3, 8, 9, I've placed a subset of nodes. However you place these in order, what's the minimum cost for that subset to be placed so far? And then what I end up doing is considering the next node I need to place. And so in front of me, I have kind of this to-do list of nodes that I need to place. So I'm just going to place the ith node in that subset of masks. And that's what I'll do here. So I just place that ith node. And then I need to calculate when I do that transition of placing that node with everything behind me, how many edges are going behind me and pointing to something that's already been placed. That's a piece of my solution I need to calculate. So that computing cost of how many things are in conflict behind me is O of n. So even though our state is our state space is O of 2 to the n, our transitions, there are only n transitions, but that calculation of the cost of a transition is also O of n. So we end up with an n squared times 2 to the n dp to solve this problem. But you can do this fairly quickly on a computer because we can use some bitmask operations. So our bitmask operation is anding the two masks of what's behind me so far, like what have I placed so far, with my edge set of what I'm currently placing. So maybe this is the edge, the adjacency list. The adjacency matrix, yeah, that's what the second piece is of what's leaving node I in terms of an adjacency matrix. If I and that with what's behind me, then I basically have the number of things that are a back edge. So it would be something like this. And if I just do a bit count on this matrix, I can do this in O of 1. So I could pre-compute all possible bit counts of every single possible mask. And then for all those possible bit counts, just do an and. So for all practical purposes, this will behave more like an n times 2 to the n algorithm, since on all input we're given, we do this operation O of 1. So that's what I'm going to do now is I'm just going to code the solution to this problem and let you see how to do this as a bitmask DP. So you have to go to a different practice room. And so this is the order of the hats problem. All right, so the first thing I'm going to do is I just want to make an adjacency matrix, basically, for every single one of these things. So spell chart.length. And so I want to make a mask for all the yeses in my matrix. If I have a yes in my adjacency matrix, I'm basically turning on that bit of what's next in my bitmask. And so that's how I do that here. And so now I have to do a DP. So you can do bitmask DPs iterative, because if you run through the masks from 0 to the at position, all subsets of this mask get computed before their supersets. So very convenient for doing iterative bitmask DP. So initially, I want to say you can't make all those changes. And my initial state is 0. OK, so if I'm at a given mask, I have to consider taking a new thing. So I want to first just check if I take this current position, make sure that if it's already been taken, to get out of here. So I want to make sure I haven't already taken this element yet if I'm adding it as my next chart. And so my next mask is going to include this element. All right. And so then I need to compute the cost of taking this element. So what I'll do is I'll pre-compute bit counts so that it's fast. I'm going to use integer.bitCount, but there's several ways you can do that. OK, so my next transition, so DP, so my result so far is just going to be whatever the DP of this mask is, plus the bit count of taking what's behind me and adding it with my adjacency list, or adjacency matrix. So I'm basically looking at all the bits that are back edges, and I'm just counting how many of those bits are back edges. I add those together. So I save the best of these two answers. And my answer is just going to be in position with everything filled in, so all ones in my mask. So I just do 2 to the n minus 1 for much the same reason. So that's my DP. I believe that should be correct. Oh, I should save n. But I am getting wrong answers. So let's see what's going wrong. Oh, yes, you have to also ensure that every single self edge is also taken. So I really should end this with next mask, because you can have self loops in this problem. So I have to make sure I pay for removing the edge to myself. And so I pass samples. So we can submit the code for this one. And you see I get all the cases correct. And it runs pretty fast, so well within the time limit. I believe some people, when they competed in this contest way back, they came close to the time limit because they had a true n squared times 2 to the n solution, which was close to the time limit. All right, but thanks for everyone for watching. And I hope tomorrow is Code Jam round 2. So if you're competing in that, I hope that you guys enjoy that. And hopefully that has some interesting problems. That's why I'm going to be competing with it tomorrow. For World Finals, if you end up seeing me at World Finals, that's great. Please say hello. I'll be walking around. I'll try to be talking to lots of people in that contest. And so I hope you guys enjoyed this episode. And I definitely will see you guys in a month. I should return. I'll post something on the Algorithms Live blog saying about when the next episode will be. But it will be in about a month because I'll be traveling so much and it'll be hard to host an episode. I'll try to post some blog items during the World Finals trip. See if there's something interesting, maybe take some pictures, that kind of thing. And then it'll be fun to go back and cover some of these episodes. So thanks for watching, everyone, and I see you guys in a month.